portion 3, we're still looking at analyzing functions, but in this learning target, we're going to justify the difference between a proportional and a non-proportional relationship. And we're going to look at when they're presented as an equation or a graph or a table. So our first one is proportional equations. So this side of our Venn diagram, which I'm going to highlight here in red, is the characteristics of proportional equations, and this side are non-proportional that I'm making in the blue color. And then what I'm going to shade here in the green is what they have in common, if they have anything in common. So our first characteristic here at the bottom is equations are written in the form of y equals mx. So that is a proportional idea. So equations are written in the form y equals mx. So for example, that would be like y. You're still going to keep your y, and then this is your slope still, so we'll say that's 3, and then x. But notice there's no value for the y-intercept. Which brings us to the second point here. Equations are written in the form of y equals mx, but they can also be written in the form of y equals mx plus b, where b is 0. So we'll just write that down. Equations are written in the form y equals mx plus b, where b is 0. So for example of that, y equals, we'll have the slope again, 3x plus, and then remember the b, the y-intercept has to be 0. So notice these two examples I gave you. They are the exact same idea, except for you don't have to write the y-intercept as 0. Okay. Non-proportional is equations, or they should say are equations, written in the form y equals mx plus b, but this time b is any, or I should say is not equal to 0. So in other words, it can be any number other than 0. So it could be y, we keep that same slope of 3, but my y-intercept, or this b right here, is anything but 0. So it could be 0.5, it can be 2, it can be 3, it can be negative 1,000. It just can't be 0, because once it's 0, then it's a proportional idea. So let's classify some of these at the bottom here. So we did all 3 of those. So it says label each of the following as proportional or non-proportional. So if you look at this first one, it looks like y, your slope is 9x, so that has to be proportional. This one, a y equals 6 now is my slope, and 5 is my y-intercept. So notice that, remember, if it's not 0, then it has to be non-proportional. Let's start that again. Being goofy on me. So y equals mx plus b. Again, that's non-proportional. And this last one, it looks like y equals mx plus b, but notice this time b is 0, and if you go back up here and look, anytime that b is 0, that is also proportional, because technically if I just cross out that 0, it turns into just y equals mx, because mathematically adding 0 does nothing. So this is proportional also. Okay, so those are equations. Now we're going to turn to graphs. So same idea, just with graphs. So we'll look down here at our list. Let's start with these last two. So the y-intercept is 0. So if you go back to equations, remember this represents the y-intercept. So if the y-intercept is 0 on a graph, that means it has to be proportional. And then over here on the other side, the y-intercept is any other value but 0. Okay. The next two that we're going to look at here is the graph will pass through the origin, and the graph will pass through the y-axis anywhere but the origin. So the origin is 0, 0, which means that's the y-intercept. So it totally makes sense that a proportional graph, that the graph will pass through the origin. So if you're a visual learner, if you think about this, we'll make a graph here. That's my x and y axes. Actually, let me make it 4 quadrants. So if it's proportional, it goes through the origin, which makes that y-intercept 0 there. On the other hand, so opposite, since this is non, which means opposite or not proportional, the graph will pass through the y-axis anywhere but through the origin. So visually, that one looks like, we'll make our 4 quadrants. So you can have any graph, so you can go like this, and notice that it doesn't go through the origin. It doesn't matter where it goes through on this y-axis as long as it's not the origin, which makes sense above because the y-intercept is anything but 0. Okay, and then the top two is maintains a constant rate of change, and the graph makes a straight line. So that is for both of them. So it doesn't matter if it's proportional, non-proportional. You can kind of see that I made a proportional graph on the left side and a non-proportional graph on the right side. And notice that the graphs are both straight. So the last point here we're going to make is the graphs make a straight line, but because that line is straight, they maintain a constant rate of change. Because remember, if the rate of change is constant, then you have a straight line. So let's kind of look at some of these examples down here. So the question is, which of the following describes a graph that represents a proportional relationship? So let's go to the proportional side. The y-intercept is 0, and the graph will pass through the origin. So it doesn't say anything about a slope, so you don't have to worry about this part, but we can look over here at the y-intercept. So the y-intercept has to be 0 to be proportional. So the y-intercept is -7 wouldn't work, the y-intercept is 0 works, the y-intercept is 8 doesn't work, and the y-intercept is 4.5 doesn't work. The next question is, describe the relationship of a graph represented by a non-proportional relationship. So if we go back and look at our information up here, the y-intercept is any value but 0, and the graph will pass through the y-axis anywhere but the origin. So any y-intercept except for 0. So again, don't matter about the slope, but the y-intercept is 3. So that's true. That works. Doesn't matter about the slope, but the y-intercept is 0. No, because that's proportional. The slope of 4/7 and the y-intercept is 0. Nope, that's proportional. And the last one, the slope is -3/4, doesn't matter, but the y-intercept is 8. That is proportional. It could be any value but 0. And the last thing we're going to look at today is tables. Proportional versus non-proportional tables. So let's look at some of our characteristics. The table could include the coordinate point 0, 0. It is not possible for the table to include the coordinate point 0, 0. So proportional goes through the origin. The y-intercept is 0, which means this is the side where the table could include the coordinate point 0, 0. Which makes sense because if it goes through the origin, that means this point would have to be in the table. Now, the word possibility just means, or could include, doesn't mean that each table has to have 0, 0, but if you force the table to move upward or downward, it would include it. So this side would be, it is not possible for the table to include the coordinate point 0, 0. Which again makes sense because if you go back to the idea of the graph, it doesn't go through the origin, which means it doesn't go through the point 0, 0. So it's not possible for the table to have the point 0, 0. The next two, so these two are done. Constant rate of change. So in a table, if we look really quick, constant rate of change means like this table is going from 0 to 6 to 12 to 18. That's a constant rate of a change of 6 here on the distance side. And then the time is 0 to 2 to 4 to 6. That's a constant rate of 2 minutes. So both of them can make a constant rate of change because they both make a straight line. So it's not like proportional is a squiggly line or something weird. They both make straight lines, so they both would have a constant rate of change in their table. And the last couple steps here, the ratios of y over x are equivalent and the ratio of y over x are not equivalent. So if you take y divided by x and it's equivalent, it's proportional. And then opposite of that on this side, the ratio of y over x is not equivalent. And we're going to look at a couple of those examples here. So look at these tables and we're going to label them as proportional and non-proportional. So one way you can tell, it kind of depends on how you want to look at it. First of all, this one's pretty obvious because right away I can see that it contains the point 0, 0, which means it goes through the origin, or the y-intercept is 0. So I can tell right away this is proportional. But you could also look at the ratio. So if we do the ratio of the y over the x, remember in a table this is x and then this is y. So in this case it would be 6 over 2. And the y here is 12, the x is 4. The y here is 18 and the x is 6. So if you simplified those, 6 divided by 2 is 3, 12 divided by 4 is 3, and 18 divided by 6 is 3. So notice that the ratio of y over x is also proving that it's proportional. The second one here, I notice right away, because remember the y-intercept is where x is 0. So this right here is the y-intercept. And remember, if the y-intercept or it contains the point 0 in any other value, then this has to be non-proportional. Okay, and we could also check the rates on this, or the ratios. So 10 over 2, or 16 over 4, as far as we have to go. You can do the rest, but 10 divided by 2 is 5. 16 divided by 4 is 4. So that's proving, again, that that's not proportional. And the last one, well, this one doesn't have x as 0, so I can see that I can't prove that it goes through 0, 0, or it has the point 0 some other value. Now, I could force it to become that, but we're just going to look at the ratio on this one, since I can't see that point. So the ratio of y over x would be 3 over 2. Y over x would be 6 over 4. Y over x would be 12 over 8, and then 14 over 12. So if we took 3 divided by 2, that's actually fractionally as far as it goes down, or you can change it to a decimal of 1.5. If we took 6 divided by 4, or simplified it down, it'd be 3 over 2, which we just see is the same thing as 1.5. And then 12 over 8 reduces to 6 over 4, which above we can see that is 3 over 2. So far, so good. They all reduce down to 3 over 2, or 1.5. But then we get to this next one, and if we divide it by 2, which would be 7 over 6, well, that isn't going to be 1.5. 7 divided by 6 is 1.16 repeating, which is not the same as 1.5. So that one almost tricks us because it looks like it's proportional. It's going really well here, but here at the end, it proves that it is, I spelled proportional wrong, non-proportional. So hopefully this helped you, and that you can look at a table and a graph and an equation and know if it's proportional or non-proportional.